last bonding theory we're going to talk about is called molecular orbital theory. And here, the orbitals are calculated for the entire molecule instead of for specific atoms. So these hybridized orbitals, I guess you could say, are shared over the entire molecule. Solving these equations is really hard. They start with a trial function, just an educated guess, and then they use very powerful computers to try basically iterating to find a solution that's close. So they're trying to find the solution that will give the lowest energy. Nature is much better at this than we are. But they find the trial function that's optimized for the lowest energy. So what we're talking about here, we don't really call them hybrid orbitals. We talk about linear combinations of atomic orbitals. That's what LCAO, linear combinations of atomic orbitals. This is just a weighted linear sum of the valence atomic orbitals in the molecule. We're going to combine those valence atomic orbitals for all the atoms in the molecule. And so those get delocalized over the entire molecule, which is in contrast to the hybrid orbitals of valence bond theory, which remain localized on a single atom. So consider H2, the simplest possible molecule. Hydrogen has one electron in the 1s orbital, and here's our other hydrogen, one electron in the 1s orbital. If we add these together, we get a shape something like this that is lower in energy than the original atomic orbitals. This is called a sigma orbital because of this shape. So we're going to use sigma and pi, and the shapes are kind of similar to what we saw in valence bond theory. So it's not something exactly new, just a slightly different. So this is lower in energy. So we call this sigma 1s. Sigma because if you look from the end of this, it's going to look like a circle, right? The next molecular orbital is made by adding the 1s orbital on the first atom with the negative of the 1s orbital on the other atom, which is the same as subtracting, right? Remember that orbitals have phases. And so if these two orbitals are out of phase and we add them together, they're going to undergo destructive interference. So this is called an antibonding orbital. It has a big node between the atoms where the electrons cannot be. This is not going to facilitate bonding. It's going to work against bonding. So this is also a sigma type orbital, because if you look at it from the end, it's still spherical. We're going to call this sigma star 1s, and this one is higher in energy. It's an antibond. So we combine two orbitals, we get a bonding orbital and an antibonding orbital. Bonding is lower in energy, antibonding is higher. So here's all of that on one slide. Destructive interference, which is like subtracting or adding the negative, we get this antibonding molecular orbital. When these are in phase, we get constructive interference and we get the bonding molecular orbital. Here we have electron density between the nuclei. This is going to hold the molecule together. Here we have an area of 0 electron density between the nuclei. That's not going to help. Any questions? So we can make molecular orbital diagrams. So on each side, we're looking at the atomic orbital for the atom, and then in the middle, we're combining those atomic orbitals into molecular orbitals. And we're only going to look at diatomic molecules, just 2 atoms, because that's enough. We just need to understand the general idea of this. So if we combine two s orbitals, we get one that's lower in energy and one that's higher in energy. In H2, we have a total of 2 electrons, one from this hydrogen and one from that hydrogen. And so we're going to put them into the molecular orbitals following the same rules that we used for regular orbital diagrams. They're going to go in the lowest energy first, and they'll pair up. So that's what we're going to get right there. And then we talk about something called a bond order, which just tells us how strong the bond is between these two atoms. And bond order is the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals, and then divided by 2. So for hydrogen, we're looking at, okay, there's 2 electrons in the bonding orbitals. Those are going to contribute to bonding. And then I'm going to subtract any that are anti-bonding, because those are working against bonding. Here it's 0. And then I'm dividing by 2 because we're dealing with 2 atoms. So this gives us a bond order of 1. If you get a positive bond order, a chemical bond will form, because that means that in forming the bond, the electrons have lower energy than they did in the atoms before the bond was formed. If the bond order is larger, 2 or 3, that means the bonding is stronger. If your bond order is 0 or negative, the bond will not happen. Let's look at He2. So again, we're looking at 1s orbitals from each atom, and they're going to make these 2 molecular orbitals, a bonding orbital and an anti-bonding orbital. But with He2, we would have 4 electrons. So we put them in here, 1, 2, and then 3 and 4. So now when we calculate the bond order, it's the number that are bonding, 2, minus the anti-bonding, 2. 2 minus 2 is 0, and you divide that by 2, and you still have 0. And this bond order of 0 says this molecule should not exist. And it doesn't, because there is absolutely no benefit to helium to do this. So it just doesn't. We can also look at diatomic ions. So He2 plus, well, He2 had 4 electrons, and if it has a positive charge, that means it lost an electron. So we can draw 2 electrons on this one and 1 electron over here. Again, the molecular orbitals are the same, but now we have fewer electrons. 1, 2, 3. So the bond order then is going to be different. We have 2 in the bonding orbitals and only 1 in the anti-bonding orbitals, and that'll be divided by 2. So that gives us a bond order of 1/2, which says this should exist. And it does. It's not common, but it can exist. So just kind of summarizing things here. We can approximate molecular orbitals as linear combinations of atomic orbitals. However many atomic orbitals you start with, that's how many atomic orbitals you end up with. Molecular orbitals that you end up with. You combine 2 atomic orbitals, you make 2 molecular orbitals. One will be lower in energy, and we call that a bonding orbital, and one will be higher, an anti-bonding. When we're putting electrons into the molecular orbitals, we're going to fill the lowest energy molecular orbitals first with up to 2 spin-paired electrons. And we're going to follow Hund's rule if we have 2 orbitals that have the same energy. The electrons are going to take their own orbital because they can before they pair up. And then stable bonds require that we have a positive bond order. And really, that just means we have more electrons in the bonding orbitals than in the antibonding. So you think of bonding and antibonding fighting against each other, and who's going to win? Right? Whoever has more electrons. So let's use molecular orbital theory to predict the bond order in H2+. So first I'm drawing the atomic orbitals. So these are the atomic orbitals. And H2+, I'm going to have a hydrogen atom and hydrogen ion, because the positive charge comes about by losing an electron. So I've got one electron over here, and this guy has no electrons. When I combine two orbitals, I get two molecular orbitals. One is higher in energy and one is lower in energy. So this is the sigma 1s. I didn't think that was so funny. And this is the sigma star 1s. So I'm looking at my atomic orbitals. I only have one electron. I'm going to put it in here. These are the molecular orbitals. And we're going to start with the lowest energy. So I'm going to put one electron in there. Done. Predict the bond order. How many electrons are in bonding orbitals? How many electrons are in this one? Looks like one. There's one orbital, there's one electron in this orbital. And how many electrons in this orbital? 0. And then I'm going to divide by 2. So the bond order is 1/2. Comparing this to H2, H2 had another electron in the bonding orbital. Does that mean it's bonding stronger or weaker? It has more electrons in the bonding orbitals. More electrons in the bonding orbitals would be stronger, right? This He2+ that we're dealing with has fewer electrons in the bonding orbitals, and so we predict that it's weaker than an H2 bond. When we calculated the bond order for H2, it was 1, and here we have a bond order of 1/2. So getting into period 2, and again, what we're talking about here are homonuclear diatomic molecules. So two atoms, homonuclear, the same nuclei, they are the same element. So things like Li2 and B2 and C2. So going to the next level, in period 2, again, we have s orbitals. And the s orbitals in the second level combine just like the ones in the first level and give us a bonding and an anti-bonding. And here's beryllium-2. So this beryllium has 2 valence electrons. Beryllium over here has 2 valence electrons. Again, combining s orbitals, we get an anti-bonding orbital and a bonding orbital. And we put the electrons in here, 1, 2, 3, 4. Now we see that there's equal anti-bonding and bonding. So I take 2 minus 2, and that gives me 0. When we get to boron, now we have to include p orbitals. So we're going to look at pairs of these combining. And we're going to call the axis between the nuclei the x-axis. So here we have the p orbitals that are on the x-axis. One lobe has positive phase and one has negative phase. And so we can add these in phase with each other or out of phase with each other, just like we did with the s electrons. So adding them in phase, we get constructive interference, we get more electron density between the nuclei. Destructive interference gives us a big node here where there's 0 electron density and pushes the electron density to the outside. So again, we start with 2 atomic orbitals, we end up with 2 molecular orbitals, one lower in energy, one higher. These are also sigma orbitals, because again, if you imagine looking down the end of it, it's going to be round. There's 2 more pairs of p orbitals. Here we have the y-axis sticking in and out of the screen, and so we can combine these positively or negatively, constructive or destructive interference. Constructive interference, we get something that looks like this, where again, we've got a lot of electron density between the nuclei, and anti-bonding, again, we have a big node. Now, these are not sigma orbitals anymore. They are pi orbitals. And then we can look at the z orbitals. Again, combining 2 orbitals, we get 2 new orbitals. And so here we have bonding and anti-bonding. This is higher in energy, and this is lower in energy. And again, pi kind of describes the shape of the molecular orbital. Now, the relative ordering of these molecular orbitals that we get from the 2p atomic orbitals is not the same for all the molecules. Boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon. But the typical ordering is that the sigma molecular orbitals are the lowest and the highest in energy, and the pi orbitals are in the middle. So this is expected or typical ordering. So here we have our s orbitals down here making bonding and anti-bonding. And then when the p orbitals overlap, we get a sigma bonding and a sigma anti-bonding. And then we get 2 pi bonding and 2 pi anti-bonding orbitals. What's different for boron, carbon, and nitrogen is that these 2 are switched. Right? Instead of the sigma being the lowest, the pi is lower. Okay, and that's not something I'll try to trick you on. The elements boron, carbon, and nitrogen are the first letters of Be Careful Now, which is a clue that we need to use the other order. Why does it do that? Well, it has to do with the amount of S and P mixing, and I'm not particularly interested in that, and I don't think you are either. So, there. Okay, so here we have the rest of period 2. This is our Be Careful Now section, where the pi bonding orbitals are lower in energy than the sigma p. And so boron 2, each boron has 3 electrons, right? So this is going to have a total of 6. So we fill those in, 1, 2, 3, 4, 5, and 6. This guy's going to take his own orbital because it doesn't cost extra. And that's Hund's rule, same rules that we followed before. Carbon has 2 more electrons, and so as those go in, they're going to have to pair up. Nitrogen has 2 more electrons, those will go in here. And if we look at the bond orders here, we see that the bond order for boron is 1. We've got 2 electrons in a bonding orbital here and 2 electrons there. I'm sorry, I did that wrong. We have 4 bonding orbital electrons and 2 anti-bonding. And so that gives us a bond order of 1. When we move over to carbon, we're adding electrons in bonding orbitals, and so that increases the bond order. And going to nitrogen, again, we're still adding into bonding orbitals, and so that will increase it further to 3. The bond order corresponds to bond energy and bond length. So nitrogen, we know from looking at Lewis structures, nitrogen forms a triple bond, and triple bonds are stronger and shorter than double and single bonds. When we go over to oxygen, fluorine, and neon, now this is the normal ordering of these p molecular orbitals. So oxygen, so we've got these guys filled up, and now we're adding 2 electrons here. We're adding them into antibonding orbitals, and so the bond order is going to go down. Oxygen has a double bond, which is weaker and longer than nitrogen's triple bond. We go over here to fluorine, adding 2 more electrons into the antibonding. Again, that drops the bond order, and fluorine F2 makes a single bond, which is lower in energy and longer than oxygen's double bond. And then here's neon. When we get to neon, we have equal numbers of bonding and antibonding electrons, and so Ne2 doesn't exist.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
The following content is provided under a Creative Commons license. Your support will help MIT Open Course.
That's nice. So that was like a super short video, right? If you want to see the longer one, you can find the link. So oxygen is paramagnetic. That's why liquid oxygen stuck between the poles of the magnet instead of pouring right through like you would expect a liquid to do, and like the liquid nitrogen did. It just went right through. Well, paramagnetism is a result of unpaired electrons, right? So this is our first example showing why molecular orbital theory is better than valence bond or Lewis theory. If we look at the Lewis model, do we see any unpaired electrons in oxygen?
Yes.
Where?
Oh, no, sorry. No, not unpaired, sorry.
No unpaired.
No,
They're all paired up, right? And here is our valence bond model, and they're also all paired up, right? We've got a pair of electrons here, and a pair up here, and a lone pair there, and a lone pair here, and then there's lone pairs on the S, all paired up. So both of these models predict that oxygen would go straight through the magnet. If we look at the molecular orbital model for oxygen, we see that it does have 2 unpaired electrons, and therefore should be paramagnetic. If we look at nitrogen, nitrogen's electrons are all paired up. It should be diamagnetic and not affected by magnetic fields. There will be a question or two about molecular orbital theory on the next exam. but I'm basically going to tell you what it is. It will be something like this. I'm going to give you this diagram and then ask you questions something like this. Like, determine the bond order for the N2 plus ion. Well, N2 plus, how many valence electrons does that ion have? Well, each nitrogen has 5, right? And there's 2 of those. And to have a positive charge, we lose an electron. So 9 electrons, right? The positive-negative thing is really confusing. 9 electrons. We don't need to mess around with where those electrons are over here, or if this one's positive or that one's positive. We can jump straight to the molecular orbitals and put the arrows in. 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you've got 2 that are at the same level, they're going to have their own orbital, and then they'll have to pair up before you can go up to the next level. So, bond order. We're looking at antibonding and bonding electrons. So that's an antibonding orbital, as is this one and this one. And this is a bonding orbital, and these are bonding orbitals. So how many electrons are in bonding orbitals? There's 2, 4, 6, 7. And literally, we're just counting the arrows. So there's 7 in the bonding orbitals, and then we're going to subtract the number in antibonding orbitals, the ones with stars. So there's 2. Those guys are empty. So 7 minus 2, and then that's divided by 2. So that's going to be 5 halves, or 2.5. And if you do that as a decimal, that's fine. So that's the answer to one question. Do we expect this bond to be stronger or weaker than an N2 molecule? Well, we're looking at N2, and it had a bond order of 3. But maybe this is an exam question, and we don't remember what it was, and we don't want to do this whole thing again for N2. The difference between N2 plus and N2 is that N2 has 1 more electron. Where is that 1 electron going to go? It's going to go in here. Is that a bonding or an antibonding orbital? It's a bonding orbital. That's going to make the bond stronger. So N2's bond is going to be stronger than N2 plus. Do we expect the bond for N2 plus to be stronger or weaker? Well, we expect it to be weaker than N2. Is this ion diamagnetic or paramagnetic? So that one's confusing, right? Because para sounds like pair, which is 2, but it's not spelled right. It's P-A-R-A. Di means 2. The animals went into Noah's Ark 2 by 2. Are these electrons going in 2 by 2? No, there's one guy that's unpaired, right? So it's not diamagnetic, it's paramagnetic. Okay? So we're looking at the formula for the thing that we've been given. And we're finding the number of valence electrons. We learned how to do that with Lewis structures. That's not hard. We're going to take that many electrons and we're going to put them in this diagram that you are given. And then we're going to identify things like, well, are there more bonding or more anti-bonding? That's going to tell us about the strength of the bond. Are they all paired up or are they not all paired up? if we look at heteronuclear diatomic molecules, things get a little more interesting. So here's the molecular orbital diagram for no, right? Oxygen's more electronegative than nitrogen. So oxygen's over on this side and nitrogen's on this side. This is more electronegative, and so its orbitals are going to be a little lower in energy. But they're still going to make the same types of molecular orbitals. Here we're looking at hydrogen fluoride, and this one's really weird because fluorine is so electronegative that its 2p orbitals are lower in energy than hydrogen's 1s orbital. And so then the molecular orbital diagram gets kind of funky looking. I'm not going to give you anything like that on an exam. So here's another exam type question. Again, giving you the correct diagram. Use molecular orbital theory to determine the bond order of the FO minus ion. Fluorine and oxygen with a negative charge. We need to know how many electrons we're going to be dealing with. Valence electrons. How many does fluorine have? 7. And how many does oxygen have? 6. And the negative one, do we add or subtract? We add. And so this is going to be 14 electrons. We do not need to mess around with these atomic orbitals on the sides at all. We can go straight to the molecular orbitals in the middle. I'm going to put in 14 arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're supposed to identify the bond order. So I'm just going to highlight the bonding orbitals. Those are the ones without stars. And the anti-bonding orbitals are the ones with stars, asterisks. So in the bonding orbitals, how many electrons are there? There's 8. Oops. And how many anti-bonding? 6? Divided by 2. So 8 minus 6 is 2 divided by 2. So this has a bond order of 1. That was the first question. Is it paramagnetic or diamagnetic? It's diamagnetic. The electrons are all paired up. So this is diamagnetic. And you'll see when you go to look at the practice exam questions that there'll be a couple of these in there, so you can see exactly what molecular orbital exam questions would look like. Any questions? Here's another example of molecular orbital theory doing a better job than Lewis and valence bond theory. We looked at ozone when we talked about resonance structures. And in Lewis theory, all we can do is draw these two structures with an arrow in between and say, well, the actual structure is a hybrid of these. It's a combination of these. It's between. We know from experiment that these bonds between the oxygens are equivalent. They are not different. Here it's shown as a single and a double, but they're actually more like a 1.5 bond. The valence bond model can't handle that either. You either have to put the double bond over here between these two oxygens, or you have to put it over there. In molecular orbital theory, those pi molecular orbitals are delocalized over the entire molecule. And so now we can have a single bond between each of these oxygens and a second bond that's spread out over all of them. So this model explains why ozone has equivalent bonds, because the electrons are delocalized. And this slide right here is really the reason we talk to you about molecular orbital theory at all. This is a molecule called benzene, which is really important in organic chemistry. It's a ring of 6 carbons with, in Lewis theory, alternating single and double bonds. So we can draw 2 resonance structures for it. But again, it's neither of those, it's in between. And so this is what molecular orbital theory shows it as. That second bond, there's 3 of them here, divided among the 6, it's delocalized over the entire molecule. And so we observe that this molecule is highly symmetrical, and it's flat, and all of the carbon bonds are equivalent to each other. They're all the same.
The electron condition freely pass between all this.
Yes.
Okay.
So the electrons here in these molecular orbitals are not limited to just being between 2 individual atoms. They can move around. They could be anywhere on that molecule. And this has a lot of, this is important because that's the resonance stabilization that we see for anything with, double and triple bonds. Not everything, but resonance stabilization can happen. And it's because of the delocalization of those electrons. So in OChem, you're going to talk about things like this and about the electrons being delocalized. And I want you to be in a place where you can say, I remember Mrs. K saying something about that. And it seemed okay at the time. So yeah, we'll go with that. Okay? I'm just showing you how and why that's possible. And I'm going to make you put some electrons, some arrows into a diagram, but that's really all I'm expecting from molecular orbital theory. This is really a high-level subject. Any questions?